The next unit we're going to start is all about what are called radicals. Radicals are more commonly known as roots, like square root is probably something that you are familiar with. So what we're going to do is we're going to start by introducing or taking a look at something that you're already used to and then adding to that knowledge. So what we want to look at first is just simplifying basic radicals. Okay, so I've got a list of radicals right here, otherwise known as roots. Okay, and we want to simplify them. This first one should be familiar to you. It is the square root of 25. Well, we all know that the square root of 25 is 5. Why? Because 5 times 5 is 25. Now, what we didn't know in the past was that when we have a square root symbol, there's actually a little 2 in the crevice of that square root symbol. What that 2 means is I need 2 of a specific number whose product is 25. The reason I bring that up is we're going to be also looking at higher order radicals. For instance, if we look at number 2 here, it's not the square root of 16 anymore. It is what we call the fourth root of 16. That little 4 in the crevice of the root sign says I need 4 of something whose product is that 16. Okay. So I'm just going to try some numbers. I'm going to try 2. Does 2 times 2 times 2 times 2 equal 16? Well, 2 times 2 is 4, times 2 is 8, times 2 is 16. So we would say that the fourth root of 16 is 2, because the product of 4 2's is 16. We can extend that into the next example right here. Example number 3. This is the third root of 64. So the third root of 64 means I need 3 of something, 3 of the same thing whose product is 64. Whose product is 64. Let's try 3. 3 times 3 times 3. 3 times 3 is 9, times 3 is 27. That doesn't work, so we need to try something different. We need something bigger. Let's try 4. Okay, 4 times 4 is 16, times 4 equals 64. So we would say that 4 is the third root of 64 because 3 4's multiplied together gives us that 64. So it's the same concept, but instead of just one number times itself, it is a number and multiple of that number. So in this case 3, in the previous example 4 of a specific number whose product is the value underneath the radical sign or the root sign. Next example here, we have the fifth root of 243. The fifth root of 243. So that means I need to take 5 of something whose product is 243. Well, at this point, we kind of start needing a calculator to do some of our work for us. So let's go ahead and get our calculator up here. I'm going to let's try 4, okay, just to see what happens. Now, I know it's going to be the wrong solution, but I want to I want to take you guys through the process of how we would do this. So 4 times 4 times 4 times 4 times 4. So I have the product of 5 4's equals 1024. So that's obviously not it. Let's try, instead of 4's, let's try 3's. Let's do 3 times 3 times 3 times 3 times 3. So 3 times 3 times 3 times 3 times 3. Does the product of 5 3's equal 243? Sure enough, it does. So here we can say that the fifth root of 243 is 3. Last but not least, we have here the third root of 216. So again, third root means the product of 3 things that is 216. Let's try 7. Okay. So 7 times 7 times 7 is too big. It's 343. So let's try 6 now. So 6 times 6 times 6 is 216. Great. So the third root of 216 is 6 because the product of three sixes is 216. Okay. So there's an introduction to higher order radicals. They operate the same way, but instead of just the product of two numbers equaling the value under the radical, it's the product of multiple, like 3 or 4 or 5 or 6 or more numbers, the product of those numbers equaling the value under the radical. So what we want to do now in preparation for our next lesson is just review / introduce ourselves to some properties of radicals and also properties of exponents that are going to help us with what we're going to be doing the next several days in class. We're going to be simplifying fairly large radical expressions. We're going to be adding them together, subtracting them, finding the products of radicals and quotients of radicals. So we want to be able to work with them and manipulate them the way we need to in order to accomplish this. So, what is a radical? Let's define it a little more specifically. Okay. The symbol that we're used to is the root symbol. The number that's in the crevice of that root symbol is called your index. Your index number is how many of a specific number do you need the product of to equal what's underneath. Well, and what's underneath the root is called your radicand. So nothing too terribly new, just defining some pieces a little bit better. You have your index, which is the number in the root, the number in the crevice of the root, and you have your a, which is the value underneath the root, which we call our radicand. So a couple properties here. Let's take a look at these really quickly. This first one, you'll actually probably know fairly well. It says for any real number a, the nth root of a to the n is equal to a if n is odd, absolute value of a if n is even. Let's put this in the context of something that you're already familiar with. If I had the square root of x squared, well, from our unit on quadratics, we knew that we undid a square with a square root. So we know that this ends up, the square root and the square undoing each other, and it simply becomes x. Now, we're used to putting a plus and minus value in front of the x here whenever we undo a square with a square root. But here what it's saying is that if n is even, instead of plus and minus, the way we're going to take care of the reality that both positive and negative are involved here is simply by putting the value in absolute value sign so that it makes it positive each time. So again, a square root undoes a square. This same principle through this property right here extends to higher order powers. For instance, if I had the third root of x to the third, well, a third root, an index of 3, and a power of 3 cancel each other out as well, so you're left with x. But you'll notice up here that if n is odd, we don't put it in absolute value signs. It's because odd exponents and odd roots, negatives are okay. You can actually have negative values there. So again, we can extend this even to higher order exponents and roots. So the fourth root of x to the fourth. What does that equal? Well, again, it just equals x because the fourth root and the fourth power undo each other. However, because n is even, just like the squared, we put that in absolute value signs. And we could keep going with this, going higher and higher order. Just remember that canceling out odd root and exponents, there's no absolute value signs. Canceling out even exponents and roots, you have the absolute value sign. Here's our next property. The next property is pretty useful in order to break up problems that we're going to be looking at in the future into manageable chunks. Okay, so it looks like this. If you have the product of two things, a and b, underneath a root, you can actually separate it into two separate roots multiplied together. So an example here may look like the fourth root of 20x. Well, underneath the radical, I have the product of 20 and x. So according to this property, I could split this up into the fourth root of 20 times the fourth root of x. Fourth root of 20 times the fourth root of x, because I have the product of 20x underneath the radical. Okay. It extends even further if you have more than one product. So I've got the third root of 16xy. I could separate this into three separate roots. The third root of 16 times the third root of x times the third root of y. So everything that's in the product underneath that radical can be separated into its own separate radical sign. But again, all the radicals are still multiplied together. Okay, two more properties to go. Here's our next one. If you have some value, some base value a, raised to an exponent of n, raised to another exponent of m, it equals your base value raised to the exponent of n times m. So an example of this would be if we had something like y to the third in parentheses to the fourth. We would call this a stacked. One way we can think of it is this is stacked exponents. So y to the third to the fourth. What does it say we do with those two exponents? If we want to combine them, we combine them through multiplication. So 3 times 4 is 12. So this would be y to the 12th. Interestingly enough, we're going to be using this the exact opposite way in the problems that we're going to be looking at. So an example of that would be if I had, for instance, y to the 8th. Y to the 8th. What does y to the 8th equal? Could I, instead of having a stacked exponent and bringing it down to a single exponent through multiplication, could I start with a single exponent and create a stacked exponent situation? Well, as long as the two stacked exponents multiply to that value, because that's how they're combined, we're good. So I could do something like y squared to the fourth, because 2 times 4 is 8. Well, I could do it exact opposite. I could go y to the fourth squared as well, because again 4 times 2 is 8. So this is the way we're going to be doing it more often, splitting it up this way. So again, you can create a stacked exponent comes to a single exponent by multiplying the exponents, or a single exponent goes to stacked exponents as long as the two new values multiply to that original value. Last exponent or exponential property we want to take a look at is similar but a little different than what we just saw. In this case, I have a base value of a raised to some exponent n multiplied by the same exact base value raised to a different exponent. If I want to combine them into a single base value a, I can do that, but I have to add the exponents together. For instance, if we had p to the fourth times p to the seventh, how could I rewrite that? I could rewrite that as a single p value because they're the same base, they're both p's. So a single p value, but what do I have to do to the exponents? I have to add them together. 4 plus 7 is 11. So it would be p to the 11th. But just like the other property, we're actually going to be using this one backwards more often. Here's how that would work. Let's say we had p to the 9th. Could I split this up into two separate p values, each with an exponent, but what does it have to satisfy? If I'm splitting it up, I know that the two exponent values that I'm splitting up have to add to that 9. So I could do p squared times p to the 7th. I could also do p to the 3rd times p to the 6th, because 3 plus 6 is 9. I could also do p times p to the 8th. I could also do p times 4, p to the 4th times p to the 5th. As long as the two exponent values add to 9, I can split p into two separate p's multiplied together whose exponents add to 9. Now it might seem a little awkward in both of these last situations to take something that is relatively simple and break it up into something more complex. But what we're going to find out is in the next section when we talk about simplifying radical expressions, that the ability to do that is actually going to be very useful for us.